Today I want to introduce the transformer, the architecture that underpins modern large language models. It changed how we build models for language by rethinking how context is captured. Over the next few slides, we will unpack why it matters and how it works. Large language models are huge neural networks trained on massive amounts of text. They often have billions to trillions of parameters and can both understand and generate natural language. Examples you probably know are GPT-4 and Claude, and older models like BERT and T5. People use them for chatbots, translation, summarization, and even code generation. Before the transformer, recurrent models like RNNs and LSTMs processed words one after another. That sequential nature made training slow and hard to parallelize, and made it difficult to learn long-range dependencies. They also suffered from vanishing gradients when sequences got long. Those limits blocked efficient scaling on modern hardware. Then in 2017, Google Research published a paper called Attention is All You Need by Vaswani and colleagues. The big idea was simple and radical. Build the model entirely on attention. That change made training fully parallelizable and dramatically faster at both training and inference. It was a turning point for NLP. The transformer has two main parts, an encoder and a decoder. The encoder digests input using multi-head self-attention and feed-forward layers stacked together. The decoder generates output with masked self-attention and attention to the encoder for autoregressive generation. Throughout, you will see components like positional encoding, layer normalization, and residual connections keeping things stable. Self-attention is the mechanism that lets each word consider every other word to build context. Inputs are projected into queries, keys, and values, where queries ask what to look for, keys represent what can be matched, and values carry the content. Attention scores come from dot products between queries and keys and are normalized with softmax. The final output is a weighted sum of the values using those normalized scores. Multi-head attention runs several attention operations in parallel, typically 8 to 16 heads. Each head learns different types of relationships or subspaces, and their outputs are concatenated. This lets the model capture diverse context patterns and makes it more expressive. For example, one head might link a pronoun to its verb, while another figures out whether bank means river or finance. Because self-attention ignores order, we add positional encoding to the word embeddings. These encodings often use sine and cosine functions to give each position a unique pattern. That enables the model to understand relative and absolute positions and preserve sentence structure. It is why the model can tell the difference between dog chases cat and cat chases dog. The advantages are clear. It processes all words in parallel, captures long-range relationships, and scales well to very large models. It is also versatile enough to handle many different tasks across NLP. Those strengths are why the transformer became the foundation of modern LLMs. The result has been a rapid acceleration in AI capabilities. Different LLM families use the transformer in different ways. The GPT series uses the decoder only for autoregressive generation. Think GPT-3 and GPT-4. BERT uses the encoder only and excels at bidirectional understanding for tasks like classification. Models such as T5 use both encoder and decoder, and newer systems like Claude and Gemini continue to build on these ideas. To recap, the transformer brought parallel self-attention, better learning of long-range dependencies, and a flexible encoder-decoder design. It opened a new era in natural language processing and accelerated AI development. And it keeps evolving as researchers build ever larger and more efficient models for the future.